Hello and welcome again to my Physical Science online video lecture supplement series. In today's video, I'm going to be discussing another of the quizzes now that you've all taken this quiz. So this is the post-quiz review for the optics and wave effects quiz. So let's go ahead and pull up the item analysis and see how you did. So on this quiz, it looks like the average score was a 58. Looks like only 15 people attempted this quiz, and it looks like you spent an average of 39 minutes on the quiz. Let's take a look at some of the ones that were frequently missed. The applying your knowledge question, I'll grant, is probably one of the more difficult ones that you have to deal with on these basically on these quizzes, because I have to modify them to begin with from the book, since they're usually an open answer, and the quiz format usually requires that I have either a multiple choice or a numerical answer or what have you. So we'll look at that one, and then I guess we'll look at this other one that roughly a third of you got right and the other 2/3 missed. That would be a mirror question, looks like. So let's go ahead and look at each of those in turn. So the first of these two is this applying your knowledge question, which says you've got two polarizing sheets. One of the sheets is slowly rotated by 180 degrees. And then it asks, what do you expect to see? So the drawing that we're talking about here would be basically something akin to this diagram from your textbook. Here, of course, is the E version of your textbook. And basically, two polarizers you can treat as you have your polarizer and your analyzer. This basically means you've got two polarized pieces of glass, shall we say, much like this pair of polarizing sunglasses. And what happens is that the light passes through the first one, gains some orientation that goes in the direction of the orientation of your polarizer. If we zoom in a little bit on these diagrams, what we see is that there's sort of vertical lines on this one and vertical lines on this one. Represents the direction of polarization. So you send in light from a light source. It has no particular polarization. It basically means that it can be oriented in some combination of these two directions. Passes through the polarizer means that it picks up an orientation that is vertical, since this is a vertical polarizer. The analyzer is basically a second polarizer that you can rotate to either match or be, in this case, perpendicular to the direction of the polarization. And what happens is that it will transmit all the light that's polarized in the same direction as it is in. This is maybe a little bit tricky to understand what's going on if you're physical science and you don't really know much about vectors, anything like that. Basically, what it means is that you could draw out any kind of a slanted line as having a part of a vertical and a part of a horizontal component. Basically, this means that you're drawing, you can represent your line or your direction of polarization as if it were a sort of right triangle. So this one right here, the polarizer, is vertical. Your right triangle is going to have a base and a height. Okay, to show a simple diagram of what's going on, imagine that I have a polarizer, and maybe the polarizer is oriented. Let's say that we just orient our polarizer horizontally like this. Now I have some polarized light, and the polarized light can be at some arbitrary direction. What this is equivalent to having, by the way, is that my polarizer that is actually doing the polarizing is rotated so that we have, maybe I should draw it more like this. So it's rotated like this, and basically the vertical lines that choose which direction the light will be polarized are like this. And then my analyzer that the light has to pass through is maybe set up more like this. So here's the horizontal lines of the analyzer. And so if you were to have light coming in at some arbitrary polarization, like this, for example, it would enter into this, and what gets lit through is light that is this way. So light that's this way then hits this, and what happens? Well, this is neither entirely horizontal nor entirely vertical. What we care about, though, is the part that is horizontal. That's the part that's going to get through. Horizontal and vertical are perpendicular to each other, so this right here is in fact a right triangle. So the part that gets through would be equivalent to the base of this right triangle, where the hypotenuse is the part that got through this. So coming down here, what does that look like? Well, if you have light that's polarized in this direction, you can again turn it into a triangle by doing something like this, where you've made a base and a height, and the base and the height are perpendicular to each other. And so the part that gets through, again, corresponds to this base. Now, what happens if we rotate the base? So we'll draw this guy again. I'm going to draw a line that is as close as I can make it to being the same length as this first line. It's a little tricky to do because I don't have a ruler here or a protractor to use, but maybe something like this is about the same length. Well, notice that again I can make a triangle out of it. Triangle looks something like this, and in both cases the part that actually makes it through the analyzer is the part that represents the length of the base. So you can see that that's a different amount in these two cases. So what is it that I'm doing to make this blue line change directions? Well, basically what I'm doing is I'm just rotating this polarizer. I'm just changing the orientation of the polarizer so that instead of having it like this, suddenly I actually have it more like this. So you can see that this is rotated a little bit with respect to the original. The black one, which is the actual analyzer, I'm again leaving alone. So I'm not actually rotating it at all. And thanks to this change in rotation, it's going to change how much light gets through. In both cases, the light that gets through is going to be like this in the polarization, but this is going to have a different length than this is because the base that I have over here is less than the base that I have over here. So now let's return to that question again. Let's look at the different options that we have. So we are rotating one of the two sheets, maybe we rotate the polarizer sheet, by 180 degrees. Okay, that means that it starts off looking, for example, like this, and it ends up looking like this. Because maybe I put a piece of tape on each end, or on one end, so that it starts off like this. Well, 180 degrees later, what I'm going to have is one that basically looks like this. I'll just draw it down here below. So here's the polarization orientation. Notice it's the same parallel to this, but this thing that started off in this corner, well, as it's rotated around 180 degrees, end up down here in this corner. So that's what a 180 degree rotation is going to look like. Now let's go back again to this question to look at what our possibilities are. It says initially virtually no light gets through, but then the light gets brighter and is brightest after completing the 180-degree rotation. Well, looking at this, we see that realistically the light should be the same brightness at the end as it was at the beginning. And that's true for any possible orientation of this thing. So we can eliminate option A, and we can eliminate option B, because option B says essentially the opposite. Initially it's very bright, and then as you rotate it keeps getting darker, and then when you've completed that 180 degrees it's the darkest. So these are both wrong. All four of these work out okay because they start off and then they end up with the same condition. So this one starts off darkest, gets brighter as you rotate it, and then ends up darkest again. Basically hits a maximum brightness at 90 degrees, then starts getting darker and finishes up dark. So that matches what is allowed. This one right here says that initially it's the brightest, and then as you rotate it, it gets darker, 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 then at 90 degrees it's darkest, and then it starts getting brighter again. And then these two both are sort of intermediate conditions. Some light gets through, some light gets through. Maybe it gets darker, maybe it gets lighter as you rotate. The reason why there's all four of these options here is because we didn't really specify how this was oriented initially. The option in which it's darkest initially basically says let's start off with the polarizer oriented like this, vertically. And the red dot that marks off a side maybe is here. Then 90 degrees later, you are going to have a horizontal orientation like so. So you can see that we go from darkest, because nothing gets through like this, to brightest. And then after doing that, you're going to end up with, delete all this stuff. You're basically going to end up going from something like this to 90 degrees later, you have something like this. And then after 180 degrees, you are back to something like this again. Sorry if the number of stripes isn't being consistent. I'm not trying to keep it consistent. It should be, but I'm not going to keep it that way. Okay. On the other hand, it's entirely possible that you could start off with something like this, where you're initially horizontally oriented, and then 90 degrees later you have a total vertical orientation, and then 90 degrees later again you're back to having a horizontal orientation. And you can see that what's going to happen here is we're going to end up starting off at the brightest. Again, recall that our analyzer that everything has to get through is oriented basically like this. This is not moving at all. So we start off with nothing getting through after 90 degrees. Most of the light gets through, and then after another 90 degrees you're back to nothing getting through. Here you start off with most of the light getting through. 90 degrees later you've got almost none getting through. 90 degrees later most of it gets through again. Okay, well, it's also possible to start off at some slanted orientation like so. So you maybe start off like this, and then you rotate it. You don't go through a whole 90 degrees, but you rotate it so that you are now like this. Then after another 90 degrees, you can rotate it to be like this, and then after another 90 degrees you are back to where you started with, which was basically like this. And you can see here that given that you have this kind of an orientation for your analyzer, basically what's going to happen is, and I guess I could draw on these intermediate steps for each of these cases. Basically, if you start off with it like this, you then have rotated it to be this way, then 90 degrees later you're like this, and then last but not least you're like this. And so we go from here to here. That means it's getting darker, then it's getting brighter. This is the brightest, now it's getting darker again. And here, same brightness. And if I rotate it the other way, so that it goes horizontal first, is basically to get brighter, gets to a brightest, then it gets darker, gets to the darkest, and then finally ends up back to where we started with. So anything that has that kind of pattern will work for the cross polarizers. Alright, so let's look at that second question. It says an object is placed 15 centimeters in front of a convex spherical mirror with a focal length of 10 centimeters. And then it asks, how far away will the image be located approximately? Stating, by the way, that if the image is real, you should make it a positive answer, and if it's virtual, you should make it a negative answer. So you can see the answer is -6. That means that it is 6 centimeters away and virtual. And again, this was marked as calculated numeric EXO11. This is straight out of your textbook. It's one of the homework questions that I explicitly assigned you from your textbook. Here is that question. An object is placed 15 centimeters from a convex spherical mirror with a focal length 10 centimeters. Estimate where the image is located and what its characteristics are. So I had to modify it a little bit because you can't really write all this for an answer to one of yours. But notice it says that the image distance is 6 centimeters and that it is virtual. So those two pieces of information are enough for you to figure out that your answer should have been -6. Now, with that said, I created a whole separate video recently by request in which I went over how to set up these kinds of questions. So I would recommend that you spend some time watching that video, because it's evident to me that even aside from not being able to get this right based on looking the answer up in the book, that those of you who attempted it are setting something up incorrectly. So let's walk through the setup of this problem again, just to give you sort of another worked example, I guess. But you should also go back and look up the other video that I already made in which I've done a similar example. Okay, we need to begin by basically drawing our mirror and making our axis and all that, sort of labeling the points of interest, shall we? Okay, so here's the principal axis, here's the mirror. Remember that the focal length is half of the effective radius of your mirror. So if this mirror were drawn as a sphere, or from this view as a circle, maybe the radius is right here. That means that the focal point needs to be right here. So this would be focal point F, this would be center of circle C. Okay, now this thing says that the focal length is 10 centimeters. So that basically means that I can draw on here little f equals 10 centimeters. And that's this distance right here. Second of all, I could just as easily put these two dots on the other side of the mirror. So I'm going to put those as x's, and that's basically, we could call this like C prime and F prime, to note that they are this focal point and the center of the mirror as reflected onto the other side of the mirror. Now, the next thing we need to do is put our object in. It says that the object is 15 centimeters in front of the mirror. That means that it's actually exactly midway between C prime and F prime. So here is the object. And again, the easiest kind of object to draw is something like this, basically an arrow. Now that we have that, the next step is to draw in our two basically rays. So one ray should run parallel to this principal axis. And the ray that runs parallel to the principal axis, if it were to reflect, should reflect in such a way that if we draw this dashed line, which runs from the center to the point where these two intercept each other, that the reflected ray will run right along this dashed line. Okay, this reflected ray is not the important thing. This dotted line that I've created here is going to be the important thing in this case because it is a convex mirror. Alright, second ray that I need to be able to draw is the ray that is aimed straight at the center of the circle. So the ray that is straight at the center of the circle basically comes through like this, and this ray can follow this dashed line. It's going to hit the circle and it's going to reflect off parallel to the direction that it came in at. So in fact I could just draw one line, but I'm drawing two to show that I have in fact drawn both my reflected and my incident rays. Where these two lines intersect is where you should be drawing the image of the object. So you can see that this image is upright. You can see that this image is smaller than the object. You can see that the image is formed here where there aren't actually two rays. There's two dashed lines. That means it's a virtual image, and that means that the image location should be negative. Now, it's entirely possible that you all drew this image using a ruler, at least using a ruler. You could use a protractor if you'd like, although I don't think it's really going to be that helpful for these kind of problems. With that said, if you drew this with a ruler and you measured all these distances out, and you measured with the ruler that this is 15 centimeters, and this is 10 centimeters, and this is 20 centimeters, then you should be able to measure from here to here, and you're going to find that you measured somewhere between, well, depending upon how carefully you did it, maybe 5.5 and 6.5 centimeters. That's pretty generous. That's almost a 10% margin of error. That's a lot of measurement error. I bet that if I were to measure this right here, I wouldn't get quite as good because I free drew this whole thing. So if you draw it with a ruler, which is what I'm telling you you need to do if you're going to solve it this way, then you will in fact find that this is about 6 centimeters. If for some reason you don't want to do the ruler and you'd prefer to try and use math to solve it, then in that other video that I made, I gave you this equation which says that 1 over dO plus 1 over di is equal to 1 over f. Now, for a convex mirror, the focal length is given as negative. So f, in fact, actually equals negative 10 centimeters. So if I want to find di, I can say that 1 over di is equal to 1 over f minus 1 over dO. So in this case, Remember that DO is the distance for the object. In this case was given as 15 centimeters. So we have basically 1 over negative 10 centimeters minus 1 over 15 centimeters. We can plug those two numbers into our calculator. 1 over 10, of course, is going to be 0.1. So let's do 1 divided by 15, and that's negative. And from that, we're subtracting another 0.1 because that's the 1/10. We get this number. Now we do, that gives us 1 over di. So 1 over di is approximately negative 0.167 inverse centimeters. So the next step is that we take 1 and divide it by that number. And sure enough, it's negative 6. So this basically means that di is negative 6 centimeters. So there we've solved it with math, and we could have also solved it with a drawing if you do this drawing and you do it to scale. So that's all that I'm going to cover in this particular video. I would strongly encourage you, especially those of you who had trouble with this second question that I just worked, to go watch through the other video as well. It gives you a little more practice with these kinds of problems. I would also strongly recommend, there's only 2 quizzes left in the class, but for those of you who are really struggling, even for those of you who don't, it's really not an issue of pride to double check your answer in the book. Please do. Please double check your answer, because I really want you guys to do well on these things. And a lot of the questions that I ask you, the answer is in fact given to you if you just look it up in the book. And it's not cheating to do this. This is an open book test. It's an open book quiz. It's not considered cheating if you want to look up your answers in the book in an open book quiz. So hopefully you are able to do better on the next couple quizzes. I will of course do a post-quiz analysis for both of those. I'm awaiting the last few people's attempts on this midterm exam. It is in fact due this week on Wednesday, unless you've made some special arrangements otherwise. So please do take the proctored exam, and good luck with that. And thanks for watching.